about it. Next week you can come up with some questions, and I'll do my best to answer them as usual. Okay, but today we're going to talk a bit about a recent kind of move in cognitive science and philosophy of mind, or philosophy of cognition, which is to move away from a more internalistic, individualistic type approach to the mind, which really wants to screen cognition off from the local environment, to one which takes cognition to be, at the very least, a matter of embodiment and being located in, or embedded in, as it's sometimes put, an environment. And a more extreme version of that, and extreme makes it sound like it's not a good position to hold, but what I just mean is extreme in the sense of where you might find them on a scale. So simply being located in an environment would be on the left-hand side of the scale. The right-hand side of the scale would be that cognition is extended, and what that means is that actually parts of the environment turn out to be absolutely critical to the way that cognition functions, and as a consequence, those parts of the environment look like they're part of cognition. So some cognitive processing may be taking place in the environment, and that's something that we would need to understand, why we would think that and how we would think that. It's actually in the last decade or so been a pretty influential position. There's certainly been a lot of robust argument back and forth regarding these kinds of explanations, primarily because the explanations themselves seem to look like competitors to a traditional kind of internalist representational theory, which had, of course, been dominant for about 20 or 30 years in cognitive science. And of course, people who hold to a particular position don't want it to get replaced by a different one which isn't theirs. So of course there's conflict. And of course people genuinely also think that there's rightness and wrongness with regard to some of these issues. Anyway, so what I'm going to do today is just outline very quickly a way of thinking about internalism. Then I'm going to look at this approach, a dynamical systems approach to cognition, which seems to show that we can think of cognitive systems as a form of dynamical coupling with the environment. Right, and I'll explain what that means. Then I'm going to talk a little bit about robotics and how some of this kind of dynamical approach has arisen out of work in a particular kind of way of thinking about robotics that was primarily kind of grounded in the work of people like Rodney Brooks in the 1990s and through even till now. And I hope I'll be able to show you a video of an example of that, but it depends whether it works. The wireless was a bit wonky when I tried it earlier. Then I'm going to go to the extended mind or extended cognition and talk about a rather famous paper from 1998 which outlines the position and look at some more traditional type of philosophical arguments and thought experiments there. Okay. So we'll start with internalism. There it is. So here's a traditional sort of picture of the mind that has been around for a while. Certainly a lot of people think that someone like Descartes held this kind of view. This kind of view seems to run across, obviously, philosophical approaches to the mind, metaphysical approaches, but also across epistemology or theory of knowledge as well, which is, in some sense, inside the head or inside the mind, if the mind isn't physical. There are things like sensations, thoughts, memories, various kinds of cognitive and mental processes. And then there's the rest of reality. Right? And reality is external to the mind. So it's an odd sort of claim because, of course, in a sense, minds and persons are in what's called the external world. Here we are. But also, this kind of position very strongly wants to make a distinction between a world of physical objects and some internal space, whether it's the brain or whether it's some sort of system that supervenes on the brain, or whether it's some non-physical essence that is somehow connected to the brain, the mind is thought of as self-contained. We make a distinction between the inside and the outside, the internal and the external. And that's also a way of setting up a traditional mind-body problem, which we're not dealing with on this course, but it's instructive nevertheless, where internal states and processes have particular kinds of properties that distinguish them from external states and properties. So in the 17th century, when these kind of ideas were getting their first formulation, people like Descartes and Galileo were introducing a primary and secondary quality distinction. So primary qualities are what mathematical physics studies. Right? They're physical qualities of objects that can be mathematically quantified and measured. Secondary qualities are things that can't be measured. They're things like the sensation of seeing the color red, or tasting, having a sensation of the taste of coffee, or something like that. Those kinds of properties are not actual real properties in the external world. They're just, as Locke later put it, mental effects of how those primary qualities affect our senses. So in that sense, the mind looks self-contained from the world. You don't actually find things like the taste of coffee actually in the world. They're mental states, and they're contained by the mind. So this, of course, leads to various kinds of problems. One, how do you explain that just in terms of consciousness and cognition and so on? But it also leads to epistemological problems about how sensations and thoughts get to be accurate representations of reality, right? Going back to the representational theory of mind. So as I said, when we looked at representation, if you go back and look at Slezak's paper, although cognitive scientists talk all the time about representations, that idea is very old. Right? It's very old. It goes at least back to the 17th century, and well, actually it goes back a lot further than that. But that's an instructive place to start. And it's just this idea that in some way there are these mental phenomena or cognitive phenomena which are ideas or thoughts, sensations, which are representational. They somehow mirror, reflect, or capture something about the way that reality really is. They're veridical. And that makes them representational. And then, of course, once you've got representations in that way, because you've made that distinction, then, well, you've got to have this whole theory of how those representations get to be true, how they get to be accurate, how they get their contents, and so on. And actually, if you go and look at empirical work in psychology and neuroscience, almost no one who's concerned with experimental work has a real theoretical model of how any of that happens at all. Philosophers, of course, have been talking about it for a while and have proposed various models of content, truth, and so on. But I guess all of them have got quite deep flaws and worries about them. So it's still a problem, and it's one that any serious science of the mind needs to address if it wants to hold to something like this picture. If it doesn't want to hold to the picture, it might not have to deal with those kind of problems, and that's what we're going to look at in a minute. Anyway, the representational theory of mind does hold to that picture. What does it say? Well, it thinks that cognitive agents, well, they're organisms, but they have internal, causally efficacious and contentful mental representations. So what the representational theory of mind thinks is that located in your cognitive system, remember the belief-desire boxes that we talked about the other week, there are states in those systems which have contents, like there's a glass of water on the table. And those states with those contents can cause various behaviors, like me reaching out, grabbing it, and drinking it. Yeah. So there's something about the knowledge states, the cognitive states, the states that are representational, that have content, that allows them to drive how the system works physically. So actually, the knowledge in the system is relevant to how the system behaves. Now you think about that, and you go back to the computational theory of mind. That's also quite a weird concept, because contents don't look like physical mechanisms that can actually physically interlock with other mechanisms and cause activity. So if you think about the way the brain's structured, and you think about the way that different neurons innervate one another with electrical impulses and neurotransmitters and so on, there's nothing there that looks like it's being driven by the content. There is a glass in front of me. All that we really get when we have a basic physical mechanical explanation is a physical explanation of discharge of ions across synaptic gates or something like that. And that looks like it's got absolutely nothing to do. This would be the Churchin's point from the section on eliminativism. It's got nothing to do with that kind of content. So the representational theory of mind does have to do a job here. It has to show how something mechanical, right? So that picture's chosen for a reason, right? We are complex mechanisms. The brain is a complex mechanism. It's broken down into simpler mechanisms. But how do those mechanical explanations, which are causal explanations, how this thing over here causes this thing to behave in certain ways, right? For those of you listening, you won't have seen me. That's the drawback of listening. You won't have seen me doing a physical motion. So what I'm trying to suggest is one separate physical object can affect another separate physical object. That's the idea. So you've got that in something like neuroscience, but what you don't have is an account of how those mechanisms themselves could be governed by contents. Contents like there's a glass of water in front of me. How could that content drive a simple machine like a group of neurons? In essence, that is the question of cognitive science. Right? If we think that we're rational creatures with thoughts and those thoughts drive our behaviors, a la Fodor, for example, then you really do need to give an account of that. And that's why a lot of people are excited about the computational theory of mind, because it potentially gives you a link between content and actual physical processes. Okay, so the second bullet point is just expressing what I've said in a bit more of a condensed fashion. So mental processes are causal sequences of tokens, token instances of mental representations. So let's move on to, jump in with questions at any time, by the way, the principle of autonomy. So principle of autonomy was suggested by philosopher Stephen Stitch as a way of limiting what we would actually explain in the cognitive sciences. So this is how he puts the principle of autonomy. The best explanation of behavior will include a theory invoking properties supervenient or dependent upon the organism's current internal physical state. So the idea here is simply that when we want to explain how any entity behaves intelligently, we only make reference to current internal physical states of that organism. We don't make any reference to the organism's past, the past states it would have been in. We don't make any reference to the environment that that organism is located in, either in physical terms or in terms of relations to other cognitive agents. Right? Often behavior is you behave in relation to others who are behaving, but this principle says that you cannot consider that as relevant. That means that really the only thing that turns out to be relevant to cognitive scientific explanation is just what I've said when we were talking on the previous slide, which is, yeah, it's just, let's look at what neurons do. Let's look at how different groups of neurons affect one another. Obviously, that's in ball terms, but really we just restrict ourselves to mechanisms that are internal. We just restrict ourselves to various circuits in the brain, and we're not interested in how those circuits might be related to the environment, other than the fact that we acknowledge that it gets input from the environment and it produces output on the environment via the body. That's it. So that's, of course, a kind of definition of reductionism. Right? It's a strongly reductionistic picture of cognition. So Fodor also strangely has a kind of version of this position which he calls methodological solipsism. So solipsism is a term which is originally was used as a kind of idea that in some way the mind could be thought of as entirely distinct from the environment. And in a kind of thought experiment style, it could be used to show that in principle minds could exist without environments. So they would be solipsistic. They would be entirely individual because they would be the only things that exist. We're not dealing with that, fortunately. What Fodor really wants to say here is that we should treat cognitive systems as if they were solipsistic, as if there was no environment. So we're not, we're not interested in whether there really is a bottle of water on the table. We're just interested in whatever internal state represents the fact that there is a bottle of water on the table. In which case, we don't need to know anything about the environment at all to be able to do cognitive science. All we need to think about is what's going on internal to the system. And that's what we should and more, as a kind of normative point, we should limit ourselves to that and only that. Fodor went on to change his mind later. Okay, so that's some principles of how you would do a strong version of internalism or individualism. There are plenty of people who still seem to adopt a position like that. What reasons might there be for thinking that such a position is a bad idea? Well, other than kind of commonsensical views, which are, hang on a minute, the environment I'm in seems to matter a lot to what I think and how I act. My relationships with others in social situations seems to matter a lot to how I think and what I do. It would be odd to say that I'm not going to consider any of that at all if I'm going to try and explain what cognition is and how the mind works, or even how the brain works. So, just very weakly, you might say, we've got to have some kind of story about the influence of the environment on the way the brain works or the way that cognition works. You could even just take a weak kind of position like that. But you might end up taking a stronger position if you thought that actually this really seriously matters. Right? We really cannot just think of ourselves as isolated individuals who function according to current internal physical states. We need to really think about what's going on, where the cognitive system or the organism is situated, what's going on in the environment, and think about it in terms of real-time unfolding dynamical behavior. Now, if you go that way, you're going to take something like a dynamical systems approach. And this has been an approach that has been developing for some time now, at least the last 20 years. There's a classic kind of collection in the mid-1990s by Port and Van Gelder. Van Gelder was a philosopher of science, an Australian philosopher of science who lamentably left the profession and went off into the private sector. But he and a linguist called Port, I can't remember his first name, sorry, put together a collection called Mind as Motion, which had a collection of papers by cognitive scientists which stated some of the basic kind of principles of how you would use a dynamical systems approach to study cognition. One thing to be said about a dynamical systems approach is that unlike computation, at least computation as you find it in computer science, dynamical systems explanations are found across many different sciences. There are many sciences that use dynamical systems accounts to explain physical phenomena and how they behave. You find them in physics, biology, and indeed in neuroscience. So some people think it's really no surprise that we would end up thinking that cognition is another species of dynamical phenomena, since there seem to be a lot of physical phenomena out there that function on, with regard to dynamical properties. Even mechanisms themselves are dynamical systems. Their behavior unfolds over time. It's not simply a single snapshot caught in time. So let's talk about dynamical systems. I'm not going to do any maths. One reason is because I'm not a very good mathematician, but the other is because we don't need to. We can just understand the general concepts of what a dynamical system is. What do we need to do to understand how a dynamical system behaves over time? So first thing to note about dynamics is that it's really seriously concerned with time. It's concerned with the evolution of behavior of a system over time. So first of all, the principle of autonomy, which says that we should only consider the current state as a snapshot, doesn't look dynamical. Doesn't look like it's interested in how a system behaves over time. Right. Secondly, then, what we'll see is that the behavior of a system over time needs to take into account what kind of environment that system is behaving in, right? And how that environment might change on the basis of the behavior of that system. Okay, two things to bear in mind. So, first of all, we need a finite number of state variables, and those just define the state of the system at a particular time. So, in a neural network, these might be, the variables might be things like units or neurons and things like axons or dendrites in terms of connectivity. So each of those variables have a function. They can behave in certain ways, and they can behave on one another in relation to each other over time, over a constant series of dynamical cycles, iterative. We need a set of state space evolution equations which describe the changes of those variables over time. So people who do the mathematics of dynamical systems are actually going to give you equations which describe how the variables in the system behave over time and how that evolution of behavior, right? And I don't mean evolution in the biological sense, evolution of behavior, how that occurs over time. So what's the behavior of the variables such that there are changes in the system over time? So here's a admittedly slightly abstract example of what we might call a coupled dynamical system. Right? So first thing is just to get the grasp that dynamical systems are about how does the variables of a system, right, how can we describe them as behaving and behaving in relation to one another over time. We need a set of equations to explain that, and then we can plot on a graph effectively, or what's called a phase space portrait, slightly more complicated, how those variables change over time, what they're doing. This is an example from a roboticist actually called Randall Beer, or as he sometimes likes to be known, Randy Beer, which I always thought was just a wonderful combination of words. So this is an example of how you could, in a more abstract sense, think of two dynamical systems interacting with one another in such a way that you think of their behaviors as coupled. Right? In other words, the two systems are constantly interacting and affecting one another's internal states and behaviors. Right? So here's a rough representation of what Beer says. Sorry, it's a lot of text, but I'll read it through. An agent and its environment are modeled as two continuous time dynamical systems. Call them A and E. A for agent, E for environment. Although we'll distinguish between A and E, so we'll say, look, here's the agent and here's the environment, sometimes we'll consider A's body to be a part of E. Well, that seems obvious. All of our bodies are located in the environment, so in a sense they're part of the environment, they're not distinct from it. However, because A and E are constantly interacting, they are described as non-autonomous dynamical systems. So hold off reading just for a minute to let me just say something about that. So this is important. You can say, look, maybe there are autonomous dynamical systems, right? Maybe there's some very, very distant planet in some galaxy far, far away in time and space that I'm not interacting with in any interesting sense, right, over time. But here what we're talking about is an agent, an embodied agent, an agent with a body that behaves in an environment such that that agent and that environment are constantly interacting with one another. You're constantly interacting with your environment in a huge variety of ways. Of course, some of them are kind of well, basically biological. So you're breathing in oxygen, various other gases, and you're breathing out carbon dioxide and various other gases. That's at least one kind of constant interaction between you and the environment. But perceptually, you're constantly receiving input from the environment. That's changing all kinds of dynamical features of your brain, at the very least, and that's also producing certain kinds of output. It might not always lead to overt behavior. But here we might just think biologically of organisms that are constantly interacting with their environments. Not only the fact that the environment gives them input, but they're changing the state of the environment by acting on it. Okay. So this coupling, right, the two non-autonomous dynamical systems that are constantly interacting, this is what we mean by coupling. This coupling is represented in dynamical systems terms in terms of a sensory function S from environmental variables to agent parameters and a motor function M from agent variables to environmental parameters. So here Beer just wants a simple kind of representation of the kinds of variables that are going to be important. So we just call sensory functions of the agent S and sensory functions of the environment, in other words, features of the environment that are going to impact on the senses of the agent S, and motor functions, or the behavior, physical behavior of the agent, we'll call it N. The two coupled systems affect one another through a constant process of feedback. An agent acts and affects its environment through M. This in turn affects the agent from the environment through S, which in turn affects the environment through M, and so on. So what you're thinking of when you're thinking of a coupled system is that there's a constant kind of feedback loop in terms of causation. So the agent is constantly causally affecting the environment is constantly causally affecting the agent. Right? Now the thing that's important about that is that, well, you know, maybe Fodor and Stitch could accept that, but the dynamical systems guys are going to say that there's a conclusion that follows from that which is explanatorily interesting and cannot be accommodated by individualists. So what is that conclusion? I'll talk about the mole cricket in a minute. The next move is an important one, which is to view these coupled systems as part of a wider system, U. A and E are components of an autonomous system, U. The state space of U contains all the variables of A and E, including S and M. And because of the higher dimensionality of its state space, a dynamical system formed by coupling two other systems can generate a richer range of dynamical behavior than could either subsystem in isolation. Therefore, U constitutes a wider system than A or E taken alone. So there's a sort of point about scope, explanatory scope here. We could just focus on A and look at A as a dynamical system on its own. And we could just focus on E and look at it as a dynamical system on its own. But when we see A and E engaged in these kinds of coupled interactions, then it's better to look at them as parts of a larger system, call it U. And then actually in A and E are not thought of as distinct or autonomous systems. They're actually non-autonomous systems because they're part of a larger system, so they become components. So here's an example of that. If you want to read a bit about this, there's a beautiful book by Scott Turner called The Extended Organism, which of course refers to Dawkins' famous book, The Extended Phenotype, where he looks at all kinds of examples of animals, organisms that are constantly interacting in this dynamical way with their environment, such that they become a coupled system. So in this case, the mole cricket burrows a little hole into the ground, and it uses that to amplify its song. Right? So it actually rubs itself against the ceiling, and it uses the vibrations to amplify out the song that it wants to produce. So there's a constant causal dynamical interaction between the created environment, which is the burrow, and the physical behavior of the mole cricket itself that produces a new behavior. So the thing that's important about that last claim here, right? You constitute a wider system than A already taken alone, but it generates a richer range of dynamical behavior than could either subsystem in isolation. Well, the burrow on its own isn't going to do much, but the mole cricket, without the burrow, and without being able to manipulate the burrow in the way that it does, interact with it, it's now got a richer range of behavior. Its behavior is, in biological terms, fitness enhancing, because it can now project its mate enticing song in a way that it wouldn't have been able to do just on its own using its current internal state, for example. So it looks like there are going to be lots of biological examples, and Turner's books is full of them, which is why it's a lovely book. So is the niche construction literature, which we looked a little bit at as an alternative to strong genetic determinism of evolutionary psychology much earlier in the course. This would be an example of niche construction. This would be an example of behaviors that organisms develop that involve this dynamical interaction with the environment to produce a behavior. And to understand that behavior, you need to consider the environmental structure and the organism as two variables, two dynamical variables of a more general system. That's why Dawkins, for example, talks about the extended phenotype, where phenotype we can consider in this case as the organism. So here's a bit from Mike Wheeler, who's a philosopher of cognitive science at the University of Stirling. If we just take this point that I'm just trying to get clear about, then what we're doing is just saying that the properties and behaviors of interacting systems of this kind are beyond the ability of either subsystem taken on its own. Well, look, say we apply that to cognition. Then the idea here would be that the cognitive unit is an unfolding dynamical system composed of what we might call broadly internal processes that interact with, broadly speaking, external processes. Vehicles here is just another word for physical variables. So the global behavior of the system is a product of internal and external processes interacting and working in concert. If we drop the internal-external speak, we just say that there are variables of two non-autonomous dynamical systems which are interacting and working in concert. They're working together to produce novel behaviors that wouldn't otherwise occur. So the idea, if that kind of moral from dynamical systems would follow for cognition, then you couldn't possibly approach cognition scientifically in the way that Fodor and Stitch are suggesting. You couldn't possibly just cut off the individual discrete organism or cognitive system from its environment if there are examples of cognition that involve this kind of dense interaction, these kind of dense interactions that produce behaviors that otherwise we wouldn't see. So, I mean, when I say you couldn't, what I mean there is, of course you can, but what you end up with is a picture, only a partial picture of the entire dynamical system, in which case you're not really modeling what cognition is in its fullest sense. Right? So, of course, you could just spend your time looking at the brain and nothing else. Right? That would be the idea here from someone like Wheeler. You can do that, and actually, there's lots of good studies of the brain on its own that are interesting and important. But the real picture of what we are as cognitive agents is going to look at neural states as only some of the variables that count with regard to cognitive behavior. The others are going to also be these interactions with other kinds of variables which are going to be environmentally located. So yeah, it's a pretty radical idea. Traditionally, most people, I guess, maybe even commonsensically, I guess, although I'm inclined to think that common sense is often ideologically driven, but never mind, let's assume that it's not. Think that the mind is just in the head in some way. You know, you look out from behind your eyes and all of your thoughts seem to be going on there, somewhere in the middle of your head. That's what it feels like. You can't see people's minds, you can't see their thoughts. They're not physical objects running around in front of them. So it seems obvious that the mind must be in the head, and I guess in sort of non-spiritualized, physical, post-20th century science, that means it's the brain. So your mind is your brain, and the only variables that could count here are neural variables. And the environment is just a location of data. It's a location of inputs and outputs, and that's it. Right. That position has been pushed for a long time. I think it's seeped into sort of collective cultural consciousness, but it could turn out to be wrong, just like many other kinds of theories that have been put forward before. So what kind of lessons might we learn from robotics? Here's Rodney Brooks with one of his favorite robots, Cog, from back in the 90s, really. What kind of lessons did we learn from robotics? Well, look, you know, of course there was a long period where people tried to do robotics by trying to develop something like a computer a la Turing that looks like it's thinking like us in the sense of our surface phenomenology of thinking, which is it looks like we have rational thoughts with content that drive behavior. So you would try to write programs for computer programs for a computer which would be the brain of the robot, which would drive the entire body and system, and it would engage in intelligent behaviors. Those kinds of ways of trying to do robotics turned out to be an abject failure by and large. But a bunch of guys decided that they would try and do something else. They thought that the way that robotics was being done was in the wrong direction. Rather than top down, you would go bottom up. So the first thing to do is to try and work out how it is that organisms move in a real environment. Right? How do they move their limbs around? I'm moving my limbs around at the moment. How do they move their arms in space? How do they reach and grab for things? We need to solve those kind of problems before we start getting robots moving around, talking to us and solving conceptual problems, or having emotional breakdowns as you get in a lot of science fiction. That's what we need to do. So you actually need sort of a lot of cool sloganeering in these sort of early papers. But one of them is we really need to work out what the cockroach brain is before we work out what the human brain is. Right? So in other words, we need to work out how it is that cockroaches are so successful, pesky little buggers that they are, escaping from those of us who wish to stamp on them. Why is it so bloody hard to get them? Why are they successful at escaping? So you need to learn something about the basic kinds of physiological process, the basic kind of sensory processes that are going on and how that drives behavior, rather than thinking that the cockroach has got something that looks like a Turing machine in its head that's giving it instructions, telling it what to do. Oh, there's a big foot coming down, quick, move left, that sort of thing. Remember intentional systems, Dennett from a couple of weeks ago. Doesn't look like intentional systems theory is going to work for cockroaches. So Brooks thinks that intelligent behavior, can only be determined, wow, that came out really bad on this, it should be read, can only be determined by the total behavior of the system and how that behavior appears in relation to the environment. So rather than thinking of trying to have some completely abstract computer system that is going to drive a machine without thinking about its body and its environment, if you just get the algorithms right, then it will behave in the right way. What you need is, you need to think, first of all, about the environment, and then you need to think about how a system physically interacts with that environment. Then you can start thinking about higher level cognition if you want to. So, back in 1991, Brooks made these kind of proclamations in a paper which are now quite famous. First is, the world is its own best model. So one of the sort of early robots, which involved a subsumption architecture, which is very simple circuitry, was to get a robot to move around the office, find soda cans, as they call them in America, so these are Americans, and to drop them into trash baskets, rubbish baskets, right? So they built this thing a bit like a cockroach, right? So a lot of the kind of experimental work that went into this has resulted in those rather wonderful, although I've never used them, robotic vacuum cleaners, right? They go around, so the robot just follows the line of walls. When it comes to, it's got a very simple laser-guided sensor. When that's blocked by something, it just then engages a very simple behavioral routine, which is to turn one way, move. If that's blocked, turn another way, move, and so on. And then when it has another kind of laser locator that finds a trash can, it just initiates a simple behavioral routine, which is to pick it up. And then it engages another routine, which is to go back to where the trash can is and deposit it. So Brooks thought that rather than trying to build a huge amount of data into the machine, which would tell it everything it needs to know about its environment, full of representations, in other words, he would use the world as its own best model. He would do what cockroaches do. Cockroaches don't have huge mental maps of every environment they're in. They just follow very simple behaviors. But it makes them really complex. It makes those behaviors, let me put it like this, it makes those behaviors more complex than you might think on the basis of the simplicity of the kind of instructions that are being followed. And also, it leads to very successful behaviors. Cockroaches will inherit the earth. So the world is its own best model. You don't need detailed representations of it to be able to get intelligent and successful behavior. Whoops. Oh well. Situatedness. Environment structure situations. The nature of the environment and the relation of the organism to that environment gives you a situation. That's part of evolutionary theory too. Embodiment. We're not talking about disembodied computer programs. We're talking about real physical organisms that have to function in real physical environments. And that's what this new wave set of robotics was about. Let's understand the physical problems, in a sense the engineering problems, before we look at a sort of more higher level kind of cognitive, representational, computational type approach. And emergence, right? So the point about the cockroach behavior is that out of very simple behaviors, more complex behaviors emerge. They can do things that you wouldn't expect. Similarly, out of the interaction of very simple kinds of circuitry, simple kinds of physical behaviors, you can get more, what look like, more adaptive and thereby intelligent responses. Now, I don't know whether I'm going to get this to work, but I'm going to give it a go. Oh, hang on. Sorry about that. If I can, I will. Oops. Unfortunately, I had to... Yeah, that's why. Hang on. This may not work. In which case, you can go and see it on its own, but... okay. Let's try just that. See, it seems to work. Ah, good, you've seen it. Yeah, it is a bit.
It just looks so unnatural. Or like, I don't know.
Well, it sort of has, it's unnatural, but it has some natural features to it. It is quite weird.
I feel like if I don't know, when I watched it, it's really disturbing on this like primal level. Like something inside you just says that should not be allowed.
Yeah. Well, let's see if it loads up. Let's hope it will. And then we'll take a break. Yeah, the wireless is quite slow today.
It's definitely worth watching.
It is, and I mean there are also quite frightening aspects of it, which are that this research. This is a robot called Big Dog, which is being designed to adapt to various environments, different environmental contingencies. It's actually being funded by DARPA, which is the military research unit of the government in the US, which has billions of dollars to spend on research. So it's being developed for military purposes. And there may be offshoots for civilian or other kinds of purposes, but primarily it's being designed as something that would be support for soldiers. Here we go. Yeah, the sound is very odd. That's Big Dog on ice. And in the snow? Not throwing snowballs yet. And then on the So I think that gives enough of a picture of, I mean, I'll just say this before we break. So, same kind of principles seem to be involved. It doesn't have detailed inner representations of the environment. It's responding to the world. Right? It's situated there. It's designed to be adaptive, to be part of an unfolding dynamical system. It's got a body. It's really embodiment is the most important thing. And all kinds of adaptive behaviors emerge out of simple interactions between environmental inputs and the internal physical dynamics of the system. So something like the Brooksian style approach to robotics has led to quite a profound explosion of real physical robots that are interacting with their environments. They're not clever or intelligent in the sort of rational sense, right? They're not doing folk psychology. They don't have reasons for acting. But they can solve complex physical adaptive problems in the way that organisms do. Right? And that requires a different kind of approach to intelligence, right? Or intelligent behavior. Okay, so let's take a quick break and reconvene in about 5 minutes or so, and I'll get on to extended minds.